So, I know this class occasionally feels like studies of the matrix 1, 2, 3, 4, and today will be no different. So, the first two things I want to do are find the E21 matrix and then find the E21 matrix's inverse. My goal for this is a little bit esoteric today. Trust me when I say that finding this kind of thing will be enlightening and will also save computer time. This is one of the days that is almost entirely applied but doesn't really seem like it. So first things first, what is my E21 matrix's result supposed to be? Like, what is the point of the E21 matrix? Yeah, I'm supposed to see a 0 right here. You guys with me on that? So the E21 matrix, I'm looking at and I'm thinking, alright, that thing's going to need to something row 1, row 2, put that thought together for me. I'm supposed to see a 0 here using row operations.
Subtract 3 times row 1 from row 2.
Good. Subtract 3 times row 1 from row 2. Is all with that? Okay, so the way that that E21 matrix is going to operate. What's it going to do the first row? Nothing, right? I should leave the first row alone. So I'm going to put a 1, 0 in the first row of the E21 matrix. That's going to leave the first row of my identity, or of my A matrix alone. You guys with me on that? Okay. Now I'm supposed to do subtract 3 row 1 from row 2, right? Let's do that. So I'm thinking that this is going to make the new row 2 the old row 2 minus 3 times row 1, right? Is with me on that? Okay, so into these two spaces, I need to put two numbers so that I have minus 3 row 1 and row 2. So how many row 2's do I want? I want 1 row 2, so I'm going to put a 1 there. How many row 1's do I want?
-3 of them.
I want minus 3 row 1's. You guys with me? So I'm pretty confident that this is the E21 matrix. How do I check that?
Apply to A.
Yeah, take that silly thing, multiply it by A, check and see. You guys all with me? So if I take my E21 matrix, I'm going to take E21, E21, and I'm going to multiply that by my matrix A. So that's going to be 1, 2, 3, 4 here. I'm going to have in here 1, 0, minus 3, 1. And I'm really hoping that's the right matrix. Might not be. I feel pretty confident though. This goes back to the philosophy of computer science. You ain't gotta break it, try something. You guys are even less likely to break it than the computer science students. You guys with me on that? Like, scribblies on paper, much less likely to destroy the universe than a computer.
I mean, it depends what's on the paper.
Much less likely. Considerably less likely to summon one of the great old ones by writing math than you are by writing a computer program. Trust me. So, this thing, I just want to do this multiplication, right? Did it work? Shit.
Let me try again.
That definitely works.
Okay, I'm going to try manually. So I'm picking this column up, twist, drop on, right? So column, twist, drop on, I get
Yeah, I did.
1.
I'm sorry.
Column, twist, drop on, 0. Column, twist, drop on, 2. Column, twist, drop on, that one's harder.
Negative 2?
-2. Did that do what I thought it was going to do? Let's see. Minus 3 times that plus that. Oh, cool.
I multiplied them wrong in my calculator, but yeah. that was my
Yeah,
first
so the order matters here, right?
Yeah.
So if you do A times E21, it doesn't do row operations, it instead does column operations or some bullshit. I don't know. It's not important today.
That was my first answer. And then I did it, and I was like, oh fuck, I did it wrong.
Yeah, it's very important to remember that the order here matters, and we're eliminating from the left. You guys all with me on this kind of thought? Okay. I need you to notice a thing here. The thing I want you to notice is that this matrix here has a special form. It's zeros down here and numbers and stuff up there.
It's like triangular.
Good. Both of these matrices are called triangular matrices because there's only a triangle of numbers and everything else is zero. This one is something triangular. Anybody got a guess for me on the term for these guys?
Is it upper triangular?
Good. It's upper triangular because very creatively, right? The upper triangle is filled with numbers and the lower triangle is zeros. On this one, this one is lower triangular. You guys with me? So here I have this kind of funny property that I've got a lower triangular matrix times my matrix A, and I got an upper triangular matrix. You guys see that? Okay. Just as a quick teaser, somebody tell me the determinant of this matrix A.
1/3.
Did you name it?
No, I did it on paper earlier.
You did it wrong.
Oh,
I
okay.
did.
The determinant. 1
Oh,
times 4.
Oh, I did it. Sorry, I did the determinant on the elimination matrix.
Ah, okay. Yeah, I want the determinant of this thing.
It's negative 1/2.
Negative 2?
The determinant
Oh,
is...
I did 1 over it.
Yeah,
I
so
was
the
trying
determinant
to
is very
reverse.
carefully AD minus BC. So in this case, this determinant's negative 2. Fun fact, notice the product down the diagonal of that upper triangular matrix? Huh. Weird. That's a fun trick we'll save for later. This is why this makes it... this is why we use this in computer science. The LU decomposition gives me a faster way to calculate determinants. Later in this book, there's a big old section about calculating determinants using something called a cofactor expansion or some goddamn thing. Suffice it to say that calculating determinants for big matrices takes lots and lots of operations, whereas calculating this LU decomposition takes fewer operations, and then you can get the determinant by looking at the diagram. Cool. Interestingly, I was super frustrated with Python, the NumPy package's way of calculating determinants, and so I wrote manually the cofactor method, and then spent some time optimizing it, and it is a bajillion times slower for big matrices. It's real bad. Real bad. The performance is awful. You can actually prove that using math, but it was more fun to see it experimentally by writing both methods and then trying it. What is the LU decomposition thing I'm talking about? So in order to talk about that, I need this matrix's inverse. You guys with me on this? Because here what I have is I have this statement. I have E21 times A is, I'm going to call this matrix U, upper triangular. You guys good with that? So I want to be able to say something like A is LU. This is what's going to be called the LU decomposition. Right, it's me looking at a matrix and considering it as a matrix L times a matrix U. You guys all recognize that in this particular case, L is going to be something?
Yeah.
What's L going to be?
Inverse of the elimination matrix.
Perfect. It's going to be E21's inverse in this case. You guys all see that? Right, I just want this over there, so I'll invert it and multiply both sides by E21 inverse. How do I know E21 has an inverse?
The determinant's not 0.
Yeah.
Yeah, from this I could say the determinant's not 0. You could also use that trick of multiplying down the diagonal to notice that any of these that you create with 1s down the diagonal is going to have a determinant of 1. That's a little bit cheating because we don't know that trick actually works, but it does, so. Okay, so I'm going to invert this matrix, and that's going to be my L. To do that, I need to actually invert this matrix. What do you guys got for me?
1, 0, 3, 1.
So in this case, you're saying that's 1, 0, 3, 1. Oh, why is that the inverse? What did I do before? Before I subtracted 3 times row 1 from row 2. What's the opposite of subtracting 3 times row 1 from row 2?
Adding 3 times row.
Adding 3 times row 1 to row 2, right? So these inverses are actually really easy to calculate. You don't even really need to get out your augmented matrix system. You just need to think about it for a hot second. You guys with me on that? So here I have decomposed my matrix A into a lower triangular matrix times an upper triangular matrix. We could further decompose A into that same lower triangular matrix. That's going to be my L. So this is L and U. I've got my matrix L. I'm going to plug in something in the middle here. And then I'm going to have a different U here. And my different U is going to be kind of same as the old U, but with 1s down the diagonal. And then anybody want to guess what this middle matrix is going to look like? I'll give you a clue. It's 0 on the anti-diagonal. Anybody guess what these two numbers are going to be?
1 negative.
1 was a good guess. What's the other one going to be? What's the other thing I had down the diagonal on the other one? Like, from here to here. Yeah, what changed is I took this -2 and kind of faked it into a 1. So this is called the LDU decomposition. It's a lower triangular matrix, an upper triangular matrix, and a purely diagonal matrix. You guys with that? So, okay, cool, I guess. Like, I did this for a 2x2 matrix. Seems like a lot of work. You guys with me on that? And it is. For a 2x2 matrix, this is a pain in the ass. It's a bunch of work. It doesn't seem particularly productive because, like, I mean, shit, the determinant calculation's really, really easy for this. The elimination's pretty easy, like, why am I doing this? And the answer is when matrices get big, then this is going to be a lot faster. So, what I'd like to do is come up with a general form for this matrix L. You guys with me on that? So let me think about a 3x3 case. I'm just going to say, alright, let's suppose A is 3x3. And I need one little condition here, so I'm going to throw a condition at the top of the board. It's just going to be, assume elimination on A doesn't take row exchange. Okay, what the hell does that mean? If you were going to do elimination on a matrix like, say, 0, 1, 1, 0, guys recognize that you're going to need to switch the rows in order to do this. Switching the rows isn't going to make this lower triangular matrix happen. You guys see that? So I'd have to do some kind of permutation thing first. It just adds a little bit of complexity. It's not particularly hard. So I'm just going to assume that's not the case here. You guys good with that? So really what I'm kind of constructing is the idea of LU decomposition for matrices that don't require row exchanges. Does that make sense? Okay. This marker's not any better than the one I gave you. So, in order to make this happen, right, I'm going to take my matrix A, and I'm going to think to myself, all right, I'm going to multiply by some stuff, right, and that's going to get me to a matrix U, right? Is with me that I could do elimination. So, here I need to know what are those elimination matrices. Like, when we do elimination, what do we start with? Got a 3x3 matrix, right? Yeah, I want to kind of start with either, and I'm just thinking to myself here, like, start with either this one or this one, and then get that one, right? So these are priority 1 and 2. You guys with the kind of diagram I've got here? I don't really care which one of these comes first. Doesn't actually matter. Which one do you guys want to put first?
I always like to do bottom left, but
Okay. And that's what I usually teach in like algebra class, so let's do it that way. So we'll say we're going to target bottom left, and then we're going to get the one above it, and then we'll get this third guy. So that first one, what's the name of the matrix that's going to do that for me? It's going to be an elimination matrix, right?
3, 2.
It's going to be E3, 1. Right, I'm going to use the pivot up here in my first row to eliminate the number in my third row, first portion. We could certainly use this number, but I'm not guaranteed that this is a pivot. Right, I'm not guaranteed that this number in the second position isn't already 0. So, because I said this could be done without row exchanges, I know that this first number is there. You guys with me? Okay, so I'm going to have my E31 matrix, so that's going to now put a 0 here. Now what? Good. I need to do this one, so that's going to use the E21 matrix. You guys with me? So I'm doing that to this whole result, right? And then I've got a 0 there. And now what's my last one? Good. This guy is the E32. E32. You guys with me on this? So, my claim is that I should be able to write A as LU. And I'm just looking for what's that L matrix going to look like. You guys see this? So I really want to be able to write A equals L, and then my U matrix. So I believe my U matrix will happen, right? Because I know I can eliminate on this thing, and it doesn't require row exchanges. So I'm going to get to a upper triangular matrix that I could do like back substitution to solve, right? What's this stuff going to be?
Inverse of all the elimination matrices.
Good. It's going to be the inverse of all the elimination matrices. Okay, except that sentence can mean two different things.
this is like decompose.
Yeah, so I can write L in two different ways. I can either take all of these, the matrix multiplication is associative, right? So I can grab all of those and say that L is the inverse of this product. Or I can invert them one at a time. Just have to be a little careful that they go backwards. You guys with me on that? So the first one I'm going to invert, if I do these one at a time, is going to be the E32 matrix. So I'm going to have E32's inverse. You guys with me on that? And then my next one
E21.
is going to be E21 inverse. And my last one is going to be E31's inverse. Or A is going to be that whole product's inverse. And if you use the whole product, it's E32 times E21 times E31. Guys with me? Cool. Okay, so this is the idea of LU decomposition. You write down the idea of elimination, and then you take all your elimination matrices and flip them one at a time to the other side. What is the thing that I've maybe glossed over or possibly lied about here? You guys see it?
There's no D.
Good, I didn't put a D matrix in here. You could do that, it won't make any difference. So that's not where I've lied to you. What have I assumed tacitly here that...
Oh, they're all invertible.
One, I've assumed they're all invertible. That I feel pretty convinced of, because they're all things like, take this row, make a new version of that row by taking some multiples of rows and adding them together. I believe that those should be invertible, for the same reason that this one was. Right, it's like pretty obvious that the reverse is just going to be adding instead of subtracting, or subtracting instead of adding. You guys with that? So where's the other spot where I might have lied to you that needs a little more reasoning here? You see that I'm grouping all this crap together and I'm calling it a matrix L? What's L supposed to be? Lower, close. Not lower diagonal, but lower triangular matrix. You guys see that? I'm like, that's a lower triangular matrix, guys. You guys believe that's a lower triangular matrix?
Possible.
Yeah, I just need a little reasoning here, right? So all these elimination matrices are gonna be lower triangular. Do you guys believe that? Like the way I'm constructing them is gonna mess with this kind of lower triangle down here. So they're all lower triangular, but I need a little something extra. I need to know that if I take lower triangular matrices and invert them, that those are lower triangular. And I need to know that if I multiply lower triangular matrices together, I get lower triangular matrices. You guys see that?
You see, like I do, show for anyone, like any variable.
Yeah, we could do that in the 2x2 case. We could do it in the 3x3 case.
Like for all cases.
So I think those are in the homework. I'm going to just right now say that those things are true, and that if you don't believe them, you should check them. And you may be forced to check them anyway, because I'm pretty sure they're in the homework. Questions about this whole thought? Okay. Right now, today, you guys are probably not super convinced that this is useful. Yes? Okay, good. You don't have to be convinced today. When we get to the cofactor way of calculating the determinant, somebody remind me and we'll revisit this for a hot second and realize that this was absolutely useful because the cofactor expansion sucks.